Okay, if you've not done these questions already, pause the video, give it a go yourself first. I will do a solution. So, Sylvia's testing a program that's been written by her friend, her colleague. Her colleague tells her that the program does not contain any syntax errors. What is meant by syntax errors? Well, there are three different types of errors that we can have. We can have syntax, we can have logical, we can have runtime. This is the one which most people experience in the early days of programming. It reduces over time, and you might have seen error messages like this. Syntax error, line 40, syntax error, missing bracket. So for example, if you were to do this, print hello, that will create a syntax error, missing a bracket. So what do we mean by syntax error? Well, syntax are the rules of the programming language. So her code, so her colleague, code will run successfully. Because if you have a syntax error, it doesn't actually compile properly your code. So if you hit run, you'll notice, even if your mistake is on line 80, line 1, line 2, line 3, line 4, line 5 will not run. It will just say syntax error, line 80. So your code will run successfully, so it can compile. What I would do then is give an example of what will cause a syntax error. An example of what causes syntax errors include missing a bracket, for example, in a print. So that is syntax error. Give the second question a go now, if you haven't already. Okay, so we've got logical errors and we've got runtime. So a logic error means the code will run, but the algorithm will not behave, that means like do, what's expected of it. I.e., if answer equals correct, dot dot, score equals score minus 1. Here's the thing, the code will run. If I hit the run button, the code will compile. So if I hit play, this code will compile, it will run. But I'm wanting score to go up by 1. I made a mistake, and it's actually going down by 1. That is an error, but that is logic. That's a logical error. We then have runtime errors. So an example of a runtime error. Well, what does it mean? Well, the program will run but crash whilst running. And that's different to syntax, because syntax will not run, it won't compile. Runtime errors will compile, but they will crash whilst running as it performs an illegal operation. So let's think of an example. Imagine we've got a text file called scores.txt, but we accidentally try and load up f equals open score.txt. File doesn't exist because we're trying to open up score, but it should be scores. So program will crash when it tries and opens it. So it'll do all the, let's imagine this was on line 100. It'll do all of the other 99 lines of code. When it gets to line 100, it will try and open up the code, up score. There's no score available because it should be scores, and the whole thing crashes. So the program will run, but crash whilst running as it performs an illegal operation. So it tries to open up a file which isn't there. It could be, another example, could be trying to loop through an array 100 times, but the array's only got 99 elements in it, or the array doesn't exist. All of those are examples of runtime. It could be that you perform a bit of math and you try to divide by 0 by mistake. Actually, no, you can't divide by 0. What will happen? It'll crash. Okay, pause the video, give this a go if you haven't done it already yourself first. So, if we want to store the average mark in a class of 40 students, but there is potential that we're going to get something like 33.3%, or raw score of 33.3. Therefore, we need to use real. There's a potential for us. Email address, that's easy, string. Number of students in a class. Integer to indicate whether an email has been read or not. So that's either going to be yes, it has, or no, it hasn't. Boolean. Nice and simple. Pause the video, give these questions a go first. Okay. An airline wants to provide passengers with information about individual flights and allow them to book their flight using an online booking system. Tick one box in each row to indicate whether this information is essential for a customer book when they're making a booking. Okay, when they're making a booking, so it's the booking. Well, they do need a time. They don't need a flight number when you're making a booking for a flight. That's what's given to you. You need to tell them what airport you're flying from. The customer's not going to put in what aircraft type. The customer's going to need to know about the ticket price and number of seats in the actual aircraft itself. Is not essential. If it was number of seats remaining, that's a different story. Okay, so this is going to be a bit of new learning for you guys. We've learned about a technique name when we're dealing with algorithms last week. We learnt about a concept called decomposition. Which is all about breaking down an algorithm into smaller steps, i.e. using stepwise refinement. But there is another technique we need to be aware of. So its brother from another mother is called abstraction. And the whole point of this is to filter out information which isn't needed when we're coding something. So let's imagine that we're coding a game. And someone gives us a wish list of 1,000 things it must do. So requirements, 1,000 requirements. And one of those requirements is going to be the game must allow, I'm trying to figure something which isn't going to be absolutely essential when we're developing our game. The car to drive. So let's imagine we've got one, the game must allow the car to drive. If we use decomposition, we can break that down into sub-steps. In one of those sub-steps is the car must move forward. But here's the thing. Does the person playing the game need to know how the car moves forward? If not, we don't need to include it in our design. We just need to know that the car needs to drive. It's quite obvious that it needs to move forward, but we don't need to know how. There's certain things where we do need to know more information, but there's certain other aspects where we don't. Let me give you another example. If we're designing a game and our game is focused on smoothness but not graphics, we could get rid of the requirement on graphics so that the developers just focus on what is essential, which is actually smoothness and frame rate. So we would use abstraction to eliminate what we don't need. This task here is a classic case of abstraction. If we're designing a website, what information do we want to give to the customer which is essential for them to see, and otherwise it might give them too much information which might confuse them? Well, departure times could be essential, flight number isn't. We can give them that at a later date. Departure airport's going to be essential. They need to know which airport we're flying from, but we don't need to know what airport. So what airplane they're going to be using. Is it a 737? Is it a 747? Is it an Airbus? Ticket price is going to be important. It's essential, but we don't need to see the customer how many seats the aircraft actually holds. So that is abstraction, what we've just done there. So you've got two different techniques, abstraction and decomposition, when it comes to planning algorithms. We've now got some experience in both. Not huge experience in abstraction. You've had way more in decomposition, but now you're aware of abstraction. And the final question, what two other pieces of essential information might we need in addition to this? Well, we need to know where we're flying to, so we need to know the destination airport. Maybe departure. Actually, we've already got departure time. Arrival time. That'll be useful. Date of flight. The seat number we're flying with. The seat availability. Because we want to know if we're making a booking, and you might have seen many websites before which have something like this, which seats are remaining. That's essential information for a customer. So all of that are different things you can put down for additional 2 marks. Nice and easy. Okay, so pause the video, give this a go first yourself, and then let's do a solution. This is actually one of my favourite questions because it shows me who is really comfortable now with the different algorithms we've looked at in the past. So we've got an algorithm to sort a 1D array, so I'm going to draw out 1D array, boom, 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 boom. And it's got values, so numbers. So I'm going to do 2, 8, 1, 6, 4, and it wants us to move the largest value to the end. So it wants us to have 8 here. And it wants us to keep repeating the process. So 8, 6, 4, 2, 1. What's that exactly the same as? You got it. The bubble sort. So all we have to do is describe how a bubble sort works. It's telling us to use stepwise refinement by basically breaking down this step and this step into more further explanation. So if we're doing it as a bubble sort, we need to have 2 for loops. We need to use an if statement. We need to use a temp. And we need an end. We want the for loop to decrease by 1 each time. And for it to be that to be the inner one, and start off with -1. So it'll be the length -1. So we didn't go outside the range. So in order for us to do this, create, or let's actually make this more structured English, assign and set variables. Let me just delete this. Index, we'll call it index2 to 0. Because remember, when we use an index in the for loop, we need to still assign it in pseudocode and structured English. So that'll be for I and for I2 in this respect. Loop through length of array. And we're going to call this outer loop. Inner loop through length of array -1 in loop 4. If inner loop index2 value is greater than inner loop value +1, then now I'm going to put in loop. So if it is greater, we need to do a swap. So we're going to put assign value to temp What else do we need to do? So assign a value to temp from index. Then what we want to do is assign current index the value from index +1, and then assign index, so it's actually index 2, my fault, index 2, because we're using the inner loop, index 2 +1, assign index 2, so +1, the value of temp. If you don't know how to do a bubble sort, this video will not make sense to you, but you should by now be able to do a bubble sort quite comfortably. So I've just done our swaps. Now what we're going to do is, I need to put in a loop, so in loop, in loop, in loop. So if no swap, and we're going to put this on the outer loop, so let's do, because I want to make it efficient, so let's have another step here. I'm just going to call it 2a. No swap equals false. Actually equals true, sorry. I'm then going to put no swap equals false. So if we made a swap, I'm going to put that in loop. And finally, if the no swap it should be no swap equals the word, not the equal sign, my fault, equals true break loop. To make it efficient, we could have used a while loop as well, but whatever, this is our flag. So I could have done this as a while loop and then just used a flag for that as well. Okay, what you need to do is turn this into pseudocode. Pause the video, give it a go yourself first. Okay, so I'm going to do count equals 1. Done. Flag equals false. Done. This is a loop. This is obviously not going to be a for loop because we're using conditions. So I could use a repeat loop, or I could use a while loop. I'm going to use a while loop. So while flag equals false and count less than or equal to 5 do. So what happens if it's true? So all of this is going to be if the code runs. So if this happens, we need to first of all call this procedure. So I'm going to do call reboot. Now my fault, I should have spelled it properly, and it needs to be caps. Done. Count equals count plus 1. Flag equals, now this is a function, so flag equals check. So we've just done our loop. Now I'm going to do this bit. This bit's not a loop because there's nothing feeding back, so it's just an if. So if flag equals false. This is a procedure. So in procedure pseudocode, we just do call. If you notice, there's a difference between our procedure calling and our function calling. Function, we put a return value. Procedure, we write the word call. Call alert 27. I should have done end while here, by the way. End while, end if. So I've just done that, and we're done. Happy days. Okay, so there are 3 questions. This question, and this question. Pause the video, give it a go if you've not done it already, and let's go through it. Apologies for the font size, by the way. I have no idea why this is like size 4 and this is like size 20, but whatever. Describe how Octopus is added to the given queue. So we have to describe, well, if I was to add Octopus, it goes into our next free position. So Octopus will be added here, which means then we have to increment end of queue pointer plus 1. And it goes into position 4. So how do I do that? Well, step 1, find the next free position. Now, do I have a free pointer? I don't, but I do have end of queue pointer. So I just used end of queue pointer, which is pointing to elk, and then looked at the next one. So by finding end of queue pointer, so EOQ, and then add 1. This puts end of queue pointer pointing to 4 now. So we're now going to be pointing to this one, and I put the data Octopus in the node. Boom. Easy peasy, lemon squeezy. Describe how the next item in the given queue is removed. So, to remove, remember, we use dequeue. So, describe how the next item is actually removed. Well, that should be pretty easy. We find the front of queue pointer. So normally it's head and tail, but we're giving us front of queue and end of queue. So we find the front of queue pointer and which is frog, and position 0, and move it to location 1 and point to cat. So increment front of queue pointer by 1. Let's just tidy this up a little bit. Next question, describe the state of a queue when the front of queue and the end of queue have the same value. So it's basically saying when these two are pointing to that. Well, this is basically saying that there is only one item in the queue. Actually, it loves using the word data item, so I'm going to put data item. So that basically means if this is gone, this is gone, this is gone, this is gone, we're going to have front and end pointing to the same thing. That's the only time that will happen when there's only one item left, because if there's no items left, they're not pointing to anything. It's null. So the only time they're pointing to the same thing in the queue is when there's only one item left. Okay, so let me just go right to the top. I want you to pause the video and give this a go, if you haven't already. Okay, so it's giving us some items in our queue, some data values. It now wants us to complete the diagram to show the state of the queue after we've done the following operations. So we've got to add wasp, add bee, add mouse, and then remove 2. Okay, so we're going to have wasp, bee, mouse. Now you'll notice that it doesn't have the front or end of queue pointer, but if we did, this would be the front originally, this would be the end of queue, so EOQ originally. We then added 1, 2, 3, so the end will now be pointing to mouse. So make that obvious, it's pointing to mouse. We then remove 2 data items. Now removing is, in this situation, we're not deleting, we're just taking and moving the pointer. So by removing 2, the front of queue goes down by 2. 1, 2. So now we've got front of queue, and you must have the pointers drawn on. So you get a mark for that, a mark for that, and a mark for adding these. Okay, interesting. Let's move down. Let me move out of the way. Let me make this a bit bigger. So pause the video and give this one a go. So the state of the queue after the other operations are carried out is now this. Complete the diagram to show the state of the queue after the following operations. Remove 1 item, then add dolphin, add shark. So let's modify this. It'll be easier for us to work on this one to make changes. We want to remove 1 item. Okay. So front of queue, let's going to go down to here. So elk, I'm going to put in brackets like that, is now gone. We're now going to add dolphin and shark. Okay, now the issue is it's just going to overwrite what's already in there because we're not going to remove anything, so we're going to overwrite. So if we're going to add dolphin, we need to take into account what's in the queue and what's not in the queue. So the queue is anything I'm highlighting now. Front of queue, we've got B in it, and we've got mouse. The rest of the items are not in the queue. It's not. This is the front, this is the end. Just because they're in this stack, you can say that these are 3 positions. So my question to you is, even though we've got ant in here, let's imagine we had a 3-pointer. Where would be the next available free space after the end of queue? It would be pointing to 7, ant. So what's going to happen is dolphin is going to override it. So now we've added dolphin to the queue. The end of queue is now pointing to here. Nice and simple. It then tells us to add shark. Now remember, queues are circular. This is a circular queue, it said it earlier. So, what's the next available free space? Well, the 3-pointer will be pointing to here. So goodbye frog and hello shark. It overwrites it. This means EOQ is pointing to here. Cat is not in our queue, fish isn't in our queue, and elk isn't in our queue. These are like 3 spaces. So you've got the end of queue here, and we've got the front of queue here. So if we're going to write it out, it would be shark, and pointing to it is the end of queue. Cat, fish, but these aren't in our queue. These are like 3 spaces. Even though we've had something in it before, there are 3 spaces not being used. Elk, wasp, so this is the first item in our queue, so front of queue. Bee, mouse, dolphin. If we had our 3-pointer, the next free space is here. 3-pointer. If you're unsure about what I've just done, you may need to watch my videos on queues, which is a playlist, abstract data types. You'll find it on my channel. Alright, we've then got our final question. The queue is implemented using a 1D array. Describe the algorithm that should be used to modify the end of queue pointer so that when we're adding an item to the queue, it updates it. It should detect any potential errors. So it's basically saying we need to create an algorithm by describing it using structured English so that when we add an item, the end of queue goes up by 1. So if I was to add a new item, let's say bird. Bird goes into here, end of queue pointer goes from 0 to 1. So, one of our steps is increment, I'm going to leave a bit of space on purpose, end of queue pointer by 1. But before we do that, if we've got cat, shark, bird, and let's put in here tiger. Let's put in here dolphin. our 3-pointer has got nothing to point to. There's no more free spaces. So if 3-pointer is pointing to null, then Q is full. So we need to check if the Q is full. There's no point trying to add something to this if there's nothing left to add to. There's no point. There's no point checking the pointers. You may as well check the 3-pointer. If the 3-pointer is -1, Q is full. If not, so I'm going to do else. 1, 2. Now, we need to also make it circular. So when, or let's not use when, if 3-pointer is at end of Q, i.e. 7, so if our 3-pointer's here, in fact, so let's change this slightly. If our 3-pointer is at, no, I apologize. If our end of Q is at 7, we need to check if 0 is 3. If yes, set 3-pointer to be 0, else -1. So basically, what I'm trying to say is this. Let's imagine our start of Q is here, or front of Q, shall I say, and our end of Q is here. In order for us to be circular, our next available free space is obviously going to be 0. So if 0 is 3, this is going to be our 3-pointer. Otherwise, if there's something in there as well, so it's not 3, that is inside here, so we've got data in it, 3-pointer will have to equal -1. So now we've got our circular Q. Another way of us saying this would be if end of Q ever becomes greater than front of Q, the Q is full. That's another way of checking to see if the Q is full. So if end of Q ever gets to there. So let's just use a 3-pointer.